So welcome everybody. We are thrilled to have Dr. Peter Bauer here today to talk to us. He's phoning from a very early hour in the United Kingdom, in Reading. So Peter is the Deputy Director of the Research Department at ECMWF, and he currently heads the ECMWF Scalability Program. He obtained his PhD degree in meteorology from the University of Hamburg. During his career, he's worked at NOAA, NASA in the United States, and IPSL in France. He led a research team on satellite meteorology at DLR in Germany before joining the European Centre for Medium Range Weather Forecasting in ECMWF in 2000. He's been a member of many advisory committees for National Weather Services, the World Meteorological Organization, and European space agencies. He is currently coordinating several European Commission projects and the ECMWF's contribution to Destination Earth. So thanks again, Peter, and we look forward to your seminar. Go for it.
Thanks 20 years almost as well.
Yes, I'd say so.
I don't remember exactly when we met, but it was certainly in the context of data simulation, obviously, and the use of difficult data like cloud and rain affected observations from satellites. Anyway, thanks very much for the opportunity here to speak to you and give this seminar. I guess I have like 45 minutes to do this, so I have like 38 slides or something. So I have to do this with a good pace. And the opportunity for the seminar is probably what's currently kind of being shared a lot as a new thing, which is called digital twins. And I'm trying to kind of explain a little what that is and why it's new and why it's not so new, you know. And in Europe, we have a program that's called Destination Earth. I want to explain what that is. And that is, for us in Europe at least, a great opportunity to develop digital twins and to exploit their advantages over present systems. But it's also like an initiative that seeds a lot of international activities and actually can international collaboration on these things, and that's why it's probably worth presenting it. So the picture here is famous, at least the left-hand side one, which is the picture that was taken off the moon's surface in 1969, back to Earth. And the right-hand side is actually a simulation of that left-hand side picture using a reanalysis. And the reanalysis is a numerical weather prediction system that uses observations and a model and combines information from simulations and observations through a data simulation system, and then recreates reality. So it's, you know, just to introduce that concept of a digital twin. And at that time, in 1969, there was no satellite data. So the only observations that went into the right-hand side picture are actually surface observations or balloons. And still, you know, the similarity between left and right is actually not bad. That shows you the power of such data simulation systems, which are the core of digital twins as well. Just an explanation. Destination Earth is a European Commission program. So the European Union has a commission. The Commission implements on behalf of the European Union big research programs and all kinds of infrastructure programs. And you may have seen that as well, that the European Commission announced a big program called the European Green Deal, which is about carbon neutrality in Europe, which comes with lots of investments, like a trillion euros worth of investments in infrastructures and technology and all kinds of things. But part of that Green Deal is also investments in research to have a better basis for making decisions, you know, political decisions or decisions how to make the economy and society greener. And weather and climate prediction are part of that. So there's a link here. They also published two other big important documents. One is a European strategy for data and a digital strategy document. And in those documents, you find what's on the right-hand side, which is, using digital twins of the Earth as the basis for information or decision support policymaking, it says here. So there is something about economic measures and societal measures for a greener society, but based on scientific information, or information drawn from science with the best possible instruments, which is the convergence of everything that we have at our hands in terms of simulations and observations and digital technology to support that transition. That's what this is about. So Destination Earth is one of the key actions of the Green Deal, and it comes with money as well. So digital twin, just to explain what that is, they have some history in industry, and the right-hand side figure shows a bit what that is. So digital twins use a continuity or a continuous merge of observations, and they do that to design production processes in industry, for example, but not just to design them, but also to monitor them and to improve their performance. So if you have a factory or something, and you replicate that factory production process in a computer, and you feed that with observations taking along that production process, actually somewhere, not temperature measurements, environmental measurements, or measurements on the condition and status of machines and all that, and you combine that in your computer, then that allows you to optimize the performance of the system as well. And if maybe there's warning signs of something going wrong, you can interfere before it actually happens. So that's what digital twins do in industry, and it's increasingly coming up also for optimizing left-hand side wind farms that design how they should work and monitor their performance. So it's about combining simulations, observations, performance monitoring, prediction. You can interact with that system. That's important. So you can change something and see what happens. And so it allows you to scenarios and intervention possibilities. So if you translate that to the Earth system, same thing, continuous combination of simulations and observations, performance monitoring, interaction, and scenario testing, that rings a lot of bells, certainly with those people who do data simulation, because that's basically what data simulation does to a certain degree. At least the first two bullets of the list here of 4, where you combine observations and simulations to produce an estimate of a state a long time, past, present, future. You can do this continuously, because continuously observations come in, the environmental state changes. We do this in weather forecasting, obviously. And then you create an estimate of the state, including uncertainties. And then you do predictions of the future. And with that system, you can also interact. You can change things. You could change a model setting, or you can change a scenario. You can add irrigation and see what happens to your water cycle, or use volcanic aerosol and see what happens. So in the end, what we have at hand from weather prediction and climate prediction is not too far off from it. Is really close to a digital twin. But how is it different to what we do today? Is it really just what we have today? We just brand it or rebrand it as a digital twin, or how is it really different? So if you look at that figure, on the left-hand side, you have the tools that are part of the digital twin. And one is Earth system modeling and data simulation, so things we do today. But it's being enhanced by certain things, So you want to integrate impact systems or impact models. So if you want to support decision making, for example, which I mentioned in the context of the Green Deal, then you want to have that scenario kind of thinking integrated, which is not part of what we do today in weather and climate, really, only in climate to a limited extent. You want to have full quality uncertainty tracing, something we do in weather to a certain degree, but there's very limited interaction in the workflows, for example. And we don't, at the bottom, really fully exploit what's called the digital continuum. So all the digital elements or technology elements that you might use. We certainly use HPC and we deal with data, but the entire set of digital technologies are not used to the full extent. But then what's really missing is that interaction with the right-hand side. You know, right now we have very linear production workflows where a weather system or climate prediction system produces data, the data goes somewhere, and then people take it up and do something with it. But there's no real interaction. So the users on the right-hand side that matter to society, they can't really interact with the system. And that's the trick here, you know, and this is what digital twins change in our concept. So there's really three reasons why they are different from an Earth system model or data simulation system. The first reason is half a reason, let's say. It's really doing what we do today, but much better. So more realistic models, better combination of simulations and observations, you know, and really try to scale that system up as much as we can. And that comes with extreme scale computing and data handling problems. So the bottom part of that graph on the left-hand side. I'm going to come to that later. But that is really the 2 and 3. So it's the full integration of the policy sectors, the right-hand side here, so water management, food management, health, and all that. And to have an open and interactive system, which is the interaction part of that. So they are different. So there's upgrade parts and there's really the parts that are different. So let's talk about these three reasons a little. So number one is this scaling up of present day capabilities. And lots of you work in climate science. You know that paper for sure. That's Ted Shepard's paper. A couple of different models. In this case, the winds to a certain forcing scenario projected to 2100, and it tells you, you know, that while these models agree on the basic heating signatures, and to a certain degree maybe also on the change on precipitation, but already less, certainly the response of the dynamics of the circulation to that heating change is vastly different, and that tells you, you know, that models simply disagree because there's lots of uncertainties in them. We certainly need a lot more realistic models. And there's a number of reasons why these models are not realistic. And right now, if you follow publications, there is like a bit of a wave of new thinking around different approaches to how we can actually improve these modeling systems. And maybe it's like 3 different schools of thought. So one is, this is like the Tim Palmer has been preaching this for a long time, and Björn Stevens as well, which is really like, you know, we have in our systems assumptions for how to represent processes that we don't resolve in our models. And we do this through parameterization. So these are approximations of subgrid scale processes like convection clouds, radiation, land surface interactions, turbulence, and these things. And, you know, their approach is saying, you know, we can deal with these parameterizations and try to tune them as long as we want, but they are approximations. And so the only way to overcome that is to lose them. And the only way to lose them is to increase your spatial resolution such that you actually resolve the process. And one of the biggest open questions here is deep convection in the tropics, because that drives obviously tropical circulation, but also global circulation. So, you know, the Ted Shepard graph I showed you before should change if you resolve convection, because global circulation will change. But that obviously has serious computing implications, because if you increase resolution, if you double resolution, your computing effort goes up by a factor of 8 or something, 10. So, you know, there's an issue. Then you have the more traditional approach, which says like, okay, you know, only investing in resolution isn't good enough. You need, or is not what you should do. You should have a more balanced approach along more traditional lines, where you say, it's really all about complexity, because the Earth system is very complex. We need to rely on parameterizations in any way. And so it's a compromise. And then you end up with probably with more like the CMIP kind of thing, where gradually you improve resolution as your computing power grows, but you rely to a very heavy degree on parameterizations. And of course, you know, that's what we've seen in the past, may not work, and is maybe not realistic enough. And then you have like a third thought, which is like, okay, resolution is important, but we probably can't afford it because of computing. And why not use new powerful tools like machine learning, or it's actually old powerful tools, but supported by new HPC technology that can help us replace some of these model components, which are presently just in the shape of parameterizations or something, by machine learning or high resolution models trained by observations or high resolution models. And then use that instead of parameterizations. And of course, there's lots to say about that, about training, representativeness and all that. So in the end, it's probably a combination of these three. But just to support the point on one, the resolution aspect one more time. This is a figure that Björn Stevens shows a lot, is where if you look at a cross-section through a convective system, and you show what the parameterization does at the bottom and what the resolved system does. So this is like an LES type or convection resolving model type. The bottom is never going to look real, and it's never going to represent the physics that actually happen on these scales in a realistic way, no matter what. So you really need to resolve processes that are presently parameterized. And if you do that, you come to you arrive at qualitatively different types of models, so parameterizations are just not going to help you anymore, just to show you that example. And some of this we actually put forward already a couple of years ago in a paper where we say, in the end, if you look back at the history in NWP and climate, the gain in skill and model realism and forecast skill and all that is in the end a summary of, or the combination of effects. It's about parameterizations, it's about coupling, it is a complex system. We need to use the power of observations and data simulation systems to teach us where the problems lie and how to initialize properly for weather. And in the end, a lot of that has a computing footprint. And because computing is increasingly becoming an issue, there's a lot of power there actually to help us overcome our key deficiencies in different ways. And that goes across scales. So left-hand side, you have model resolution on the x-axis and complexity on the y-axis. So it's a bit of a deviation of this classic resolution and timescale graph. So the challenge is, if we want to go to the left, so increase model resolution, computing is this light pink box is increasingly becoming the key challenge to overcome. So computing is certainly one thing we must deal with if we go into digital twin space, for all the three reasons. So reason number two, this was about full integration of policy sectors. You have increasingly papers coming up explaining that a bit more. I mentioned earlier that we have right now these more linear value chains, climate models, weather models produce data, put them somewhere in a database, then people pick it up or they understand it or not. There's a lot of translation science going on, interpreting this data for non-experts, so non-climate scientists or weather scientists. Increasingly, that has to come together more, and deviate more from this linear flow. So increasingly, climate science or weather science has to become aware of what the data is actually being used for and change workflows and the setup of simulations and simulation systems such that using it or using the information and changing the system if climate services require is more easy. And secondly, we need to understand better where the deep uncertainties lie in these systems so that we actually can interpret those better and propagate those better into the impact science, so social science, economics, whatever, so that needs a rethinking. Then there's also another recent paper, primarily Australian, I think, and a number of you are actually on it, which also talks about this in a different way, where you have the more linear workflow shown on the left-hand side, again, mostly a research community setting up experiments and systems for their use, for expert use, driven by certain scenarios and then everything else that happens on the society relevant side is downstream, and there's no arrow going up in any way. And in the future, you need to drive this in a different way, where actually the owners of the services or the users of the services define what they require in a much better way, and that you then set up systems that can respond to these requirements in a much more flexible way. You will still have the benefit for research because that doesn't change, that only can go better, become better. But at least have the possibility to turn around these workflows and empower the recipients of this information. So this is very important, and that's an integral part of the of digital twins. So, you know, then that allows you to deal with environmental information in a different way, you know. And if you look at, you know, the ocean, for example, you can then really go across scales and across different components of these systems. You can ask very specific questions, which right now are difficult to ask with these traditional systems. For example, what's the most sustainable way to capture wild fish? Because you can play with that system. Or what's the most cost-effective option to mitigate the coastal impact of sea level rise? You know, so all with the same system, but all with that logic of digital twins and the level of interaction. Can ask similar questions for solid Earth. I picked examples here that I don't have in climate because, of course, you know, you're familiar with those. But just to show how translatable and transferable such a system is to all kinds of questions. So seismic response to geothermal energy harvesting, certainly important for the Green Deal, or impact of catastrophic volcanic eruptions from climate, for example. It's always important to think this through in terms of these information chains. And the important here is the title, you know. What we want is we want to create the right data so that we can extract the relevant information for it. And what relevant information is depends really on what you're looking at, whether you're looking at health or food or water or civil protection, to then gain insights and then make decisions. And that will only work in a much more flexible setup, you know, so that you can walk through these chains of events from a certain, you know, regime in the atmosphere to the impacts on weather. In this case, a combination of heat waves and droughts. And then whether you look at vegetation in terms of crop failure or agriculture policy making, or forest fires and civil protection and all these things. So it's really important to think through all these possible connectivities to make the best use of data, you know, that we right now treat more anonymously. And then reason number 3 was about interaction, you know, and it's really about, if you look at the right-hand side, you have a digital, ideally what you want is to have a digital twin framework somewhere that does all the technical work for you, that deals with what's under the hood in everything I mentioned before, and then that you have, and that uses observations and simulations and this interactive workflow kind of thing. And then all kinds of users can actually play with that. You know, they can, of course, to a certain limit, because you don't want them to violate science principles and all that, to be done in an educated way. And certain things are probably unable to change for non-experts. But you want to have a much more flexible system that allows you to turn around this workflow and flow of information that I mentioned before. You know, whether it's somebody looking at storm forecasts, or somebody looking at forestry, or somebody looking at agricultural policy making, for example. So it's all about a holistic approach, and that you can address science and application questions at the same time. And obviously, you know, because this is a complex machinery, it requires significant investments in digital technology, and some of it is big computers, but probably even more is an investment in software systems. I'm going to come to that. So increasingly, this concept, so these 3 reasons and the digital twin thing is actually getting increasingly some traction in the community. So that you have these different schools in modeling, I explained earlier, but increasingly you see that these ideas of you know, we need an upgrade in all these 3 directions to really change something is becoming more popular. And this is an example here on the right-hand side in red of 12 white papers that have been published a couple of weeks ago by the Royal Society prior to the COP26 conference that's going to happen in Glasgow later this year, where you see these similar terms, you know, like at the bottom, create digital twins that simulate and optimize sectors of the economy to reduce carbon emission, for example, or kilometer scale, kilometer simulations, exascale computing. So a lot of the that I mentioned before are achieving some or receiving some support in the community. Also, in bodies that tend to be a bit slow sometimes. So there's the WMO, World Meteorological Organization, that has the World Climate Research Program, WCRP, that's presently reformulating its research directions, or emphasizes certain research directions, for better decision making and for faster progress. And one of those is called Digital Earths, which is not too dissimilar from what we've just been talking about. And at the core of this sit advanced digital technologies, what I just mentioned before, and for the particular purpose of climate prediction, and to operationalize that more and to make these workflows more interactive and bring skills together that we traditionally have in NWE, for also make that increase the society, focuses on the use of data simulation for climate models, for example, this extreme scale simulations and applications like Digital Earth or Digital Earth in Australia, for example, with these upgrades shown in black. So increase that is receiving attention, and so it's worth looking into this in more detail. So I mentioned computing. And obviously, if you go to very high resolutions and you create these very interactive systems, that comes at a cost. And we've done a lot of experimentation around that to understand actually what that cost is. And one simple thing to do is, or comparably simple thing is to do is you take an existing system like a climate model or a weather model or a weather data simulation system, and you scale it up. So you run that at a kilometer as opposed to 10 kilometer, which is like what most global centers do today. And then you run this on very big machines and you see how much that costs. And it gives you an indication of a benchmark of the cost for the future. And we did this with the biggest computer in Europe, which sits in Switzerland a few years ago. And we also did this, and are still doing it, on Summit, which is the biggest machine right now in the US and the second biggest in the world. And we ran nations and did an estimate of how fast we could actually run these simulations if we take as much of these machines as we could. And our estimate says that if you would run a system like this on a big machine, you're probably a factor of 100 too slow still, even if you use such a system. So it's not just buying bigger computers, it's really investing in changing something in your simulation framework to actually reach efficiencies that make digital twins at those scales realistic. One thing is you need big computers, no question, but increasingly, I don't know how many are into computational science, but or technology. There's a big change coming right now. Computers are getting bigger, but they're also becoming more complex. And they're becoming more complex because traditional processor technology and memory technology isn't just increasing as much anymore as it was in the past. And most of you have heard of GPUs, so graphics processing units that became hip when video games became hip. And they have actually HPC potential, but that's a different type of processor that needs different types of programming. And it's a big effort to change your codes to run on these processors, but there's other types of technology coming as well. So it's not just GPUs. So increasingly, computers are becoming more complicated. And that has implications on code design and all that. And what we did at the beginning of this year, we tried to recognize that and said, like, if you want to achieve these scales, so kilometer scale, let's say, so you want to have uncertainty estimates or ensembles or some other technology. You want to achieve that at the same time. And on the left-hand side, you want to have enough throughput with your code that you can make your simulations run your simulations fast enough. You want to move between machines, so not be restricted to a single technology. And you want to have a system, a resilient system that performs 24/7. The only way to do this with modern technology is to invest in at least, we categorize this into 4 areas, and you have to invest in those all together, not individually, but all together. So they all have strengths and weaknesses in certain parts of these 6 axes. But you need to invest in and ask questions again about your fundamental design of systems in terms of numerical methods, algorithms, the way you represent data in your systems. Machine learning offers you something. You certainly need to look at programming. I mentioned programming in the context of GPUs. So you have to change programming models, which is really, really hard, given our old heritage codes. And you certainly want to exploit everything that's on offer now in terms of technology provided by GPUs and FPGAs and whatnot. So, but it takes an investment in the 4. And this is really radical and different and requires significant work and investments to make that work. And this is why we call it the digital revolution. It's not just a little code change here and there. It's really redesigning a system, otherwise it won't work. So one thing about computing is that computing alone isn't good enough. Big computing creates big data. And you probably have seen this. So these are the 3 V's or 6 V's of big data. So volume increases, variety increases, velocity, so the speed at which we create big data, but also veracity, value, and variability of data changes. So the left-hand side is more about the engineering aspects. So this is really more about, how much do we produce at what speed and how diverse is the data under the hood. And the right is really more about what we take from the data. So this is more about what I said earlier in this headline, turning data into information, into insights, and into decision-making. So how do we actually extract what we want from the more engine plumbing side on the left-hand side? So we have to deal with these 6 V's at the same time. And if you look at what we're dealing with today or in the future is, we're using already in data simulation systems today about 100 million observations per day, for example. That is going to grow, certainly by a factor of 10, maybe 100 in the next 10 years. If you look into IoT data, so if we add data from mobile phones and CCTV cameras and car sensors and all that, the volume is just going to explode, as will the variety at the same time. We probably expect digital twins to produce off the order of a peta to 10 petabytes per day. Right now in our system at ECMWF, we have about 150 terabytes per day. That's already a lot. But 1 or 10 petabytes per day require entirely different approaches to data management, dissemination, and lifecycle management as well. And then the trustability of data will diversify as well. You can't ask on the 5th floor as much as a well-designed satellite instrument with great calibration environments in orbit. The business value can only grow because if we have digital twins with this much tighter link between science and impacts and applications, then the value that this data generates in terms of information, insights, and so forth is just going to explode. So these are the 2 right-hand sides. So there's basically no limit to that. One thing I should say in the context of computing and data is energy usage. You might have seen, if you are vaguely familiar with this, is that these big computers, they cost a lot of power. They cost a lot of money to buy in the first place, but then to maintain them and run them costs a lot of power. So our machine today we have in operations is probably that the electric power cost at ECMWF is roughly 6 million euros a year. And you want, of course, it's a good investment, no question, but you want, of course, to draw power from an environmentally sustainable source, which is presently not the case for us, for example. But in the future it will be. So increasingly, as you buy big systems, occupy or consume more power, even though, and this is what the y-axis is here, is they become increasingly more efficient as well. This is from the top 500 list in green computing. So increasingly, this upward trend indicates that the system produce more performance per watt that you power them with. But still, these systems use a lot of power overall because you want much more. And one other thing I should discuss that it's not just about the energy used in computing, because in the end, most of the energy is actually used moving to the computing power. If you go to the right and you move data on the chip or away from a chip across a big machine, for example, your electric power usage grows exponentially. So a big part of that power envelope is actually moving data. So that needs to be in the back of our mind. So it's not only about computing; it's actually more about data. So I found this, just a little anecdotal from some presentation, summary of 10 commandments of big data, for example. We don't have to focus on them, but some obvious things. Don't move data. Move the computing where the data lies. You need clever hierarchies to kind of do calculations with as little data movement as possible, which I just mentioned before. And in the end, it's a lot about intelligent tools. So machine learning actually plays a big role in that side where you are sit at the interface of running some compute job, and then you produce data and want to do something with it. And just to show I cover two items here. One is about compression, so that you actually reduce the data that you are moving. And intelligent compression algorithms do exist. Some are lossless, some are lossy, but there's different ways of representing data to actually help. So simple technical things can actually help you to reduce that data overhead. On the right-hand side, it's more on the output side, how you can compress data and still retrieve most of the information you're after. So that plays a big role, just reducing the sheer volume of data. And the other is about clever extraction of information. So we mentioned machine learning and the generation of information from data and deriving insights from that. So it is about not using machine learning as a black box and just applying some algorithm to a big load of data that sits somewhere, but use what we know about the system so that we understand causation, for example. So what causes what for good reasons and reasons that we understand. And this is about a very, there you need to combine your Earth system domain science knowledge with technical knowledge about what you're after to actually understand what's happening in the system, even if you have to grind through a lot of data. And these are just examples from a single publication here. On the right-hand side is, you can apply this to global circulation and the connectivity of surface state, tropospheric dynamics and stratospheric dynamics to understand teleconnections, or how sea surface temperature drives ecosystems near the surface, for example. So in the end, it's a lot about digital technology, and part of that paper that I mentioned earlier, we actually propose which areas we need to work on. And I mentioned that it's basically everything. This is why it's radical and why it's called a revolution anyway. So you have to touch everything in your prediction chain to really run these systems at those levels at the good scales with that level of interactivity. I don't have time to go through this, so I just direct you through that paper, have a look at it. Yeah, but you have to basically touch everything to be able to use these fancy new technologies. And I mentioned EuroHPC on the right-hand side because I use this figure in Europe a lot to kind of say that we really need a new generation of computers that the European Commission is funding as well to be able to deploy these systems. I probably want to skip the last 4 slides for the sake of time because I think we're at 45 here, but I have a couple of slides that I usually introduce talks with that show the importance of what we're doing. And I'm sure all of you know that, but it's always good to have some figures. So I'm going to go through this within 2 minutes here. This is from the World Economic Forum. They do this every year, and they show the importance of risks shown in a graph here. On the x-axis likelihood and on the y-axis impact. And you don't want to be in the top right corner because that means it's very likely to happen. And if it happens, it has a very big impact. And in the top right, you have climate action failure, biodiversity loss, human environmental damage, and extreme weather. And all of those are actually targeted by this digital twin configuration that we're increasingly talking about. So it's the right things for the right reason. And then we don't have to convince ourselves about the impact and the cost of climate change and measures climate adaptation. But I mentioned the European Green Deal investment is $1 trillion. You know, so all this investment in the green economy just in Europe is $1 trillion. So what is an investment of, let's say, a couple of 100 million or $1 billion even on information technology that helps you drive it? I would, you know, at the top, you know, if you look at the cost of achieving sustainable development goals, it's many hundreds of billions per year, you know, by 2030 in this estimate from the United Nations Environmental Program. And later, the further you go, it becomes more expensive. You know, so any investment is basically worth doing. You can do the same for extremes. This is from the United Nations as well. Just shows the statistics of billion-dollar disasters, of which there were 120 in the last 40 years. And you can look at the statistics. Don't have time now, but you know, I just point you to these documents, and always the important statements to make. You know, all this cost is tremendous, and the investment are tremendous. And if you invest in HPC to help you, or digital technologies to help you, the factors with which you get the payback are tremendous. You know, any euro or Australian dollar you invest in digital technology, you get back 50 times over or 100 times over. So no question. So just to summarize, the digital twin is not entirely new, but new. So it scales up everything that we do today, but it brings it together in a much more holistic way. I hope that message worked. So it is all about scaling up and using supercomputing and all digital technologies to allow you to do that in an affordable way, but then making the important step of linking the impact sectors in and adding this large degree of configurability so that you move away from these linear value chain. That, of course, requires investments in technology and bigger computers, but mostly it's actually in people. Because what we mostly need to fill in is these intermediate areas, so expertise between Earth system science and the classical weather forecast and climate scientists and impact sectors. And the same for, you know, the computational science aspect, so people that help us redesign our systems, so computational scientists who care about weather and climate and not so much about Google, even if it's half the salary, and are ready to help us design our digital environment such that we can make it work like this. And as I tried to show with the previous 4 slides, maybe funding is not really the issue here, given the value of what we do. And with this, I'm finished and take questions. Thank you.
Thanks, Peter. That was really interesting. So we have one question in the chat already. I don't know if you can see that, Peter, but it's from Ian Macadam. And Ian, feel free to jump in if you want to show yourself. But it says, how do we evaluate digital twins involving the climate in the context of informing decisions? I guess he's looking for some examples.
Yeah, I'm just conscious of,
yes.
of when I read an IPCC report on let's say evaluating global climate models, there's statements about maybe CMIP6 has improved relative to CMIP5, but that kind of evaluation would seem to me to have little usefulness for informing decisions.
Yeah. Yes. Is it me or is it...
I think it's you, Peter.
You I think I got the question. Yeah, it could be me. I hope it doesn't. Yeah, I hope it didn't happen during the presentation too much. Anyway, okay, so there's a lot to say about CMIP and whether that approach is the right approach, and whether, you know, as you diversify models and add more models and sub versions of single systems, if that helps. There's certainly a trend that where you can say, you know, the models, they do improve. Whether CMIP is properly reflecting that is a question, you know. But what we're asking here is a deviation from this. You know, it's a really different philosophy. It's not about a democratic multi-model exercise as much as, you know, just promoting fewer leading systems, but by a step change, you know, and then adding everything I say. But it's I think your question is actually more basic than that, because in the end, you know, if you have a system that includes impact sectors so much better than present systems do, you also have more opportunities to verify and validate, because, you know, you don't only look at temperature and precipitation and things, but you can also look at verification in areas that matter, you know, in terms of wind energy or river flow or something like that, you know. And you can create that over past, you can verify this over past periods, but it's very similar to NWP systems here. If you take an NWP systems and you verify your rainfall with a gauge, and then you add to that verification, you know, plant growth or river flow or other systems that are part of that system, it just expands your opportunities for verification by so much more. And so by adding such components and these impact sectors, I think you actually add information, add opportunities for new observations to help you improve the entire system, and actually show that you improve for the right reasons. Because you know, we tend to, and I think climate models suffer from that. The present generation climate models suffer from that. A lot of them produce very wrong weather. They produce decent climate predictions, but very, very wrong weather. And so that tells you something about producing good results for the wrong reasons. They're you know, and that's an issue. And this is where NWP and climate and these digital twins have to come together to make sure that, you know, what they produce in terms of results at climate timescales are happening for the right reasons. And you can show that if you verify climate models on weather timescales, for example. So if you have a digital twin environment, it would allow you to do that.
Yeah, great point, Peter. Adding more complexity enables you to look at more things to see if things are behaving like reality or something else. Claire Vincent has a question precisely about this. She says,
yes,
just come on, show your face, please. But she says, as we add more layers of complexity to modeling systems, I guess the uncertainty will also increase. If we had an ensemble,
it probably does. Yeah, no, it probably does, and I don't know what how big the ensemble needs to be, and there's also affordability issues. For example, you know, if you invest in a global scale simulations, you will not. And I showed you something about the cost. You know, you will not run 1,000 members or 100 members of that. You know, so we certainly have to make sure that we take uncertainty estimates along. There will be more degrees of freedom, so there will be more reasons to have added uncertainty. But I would argue that may be, but we probably have a more realistic uncertainty estimate, because we resolve more of the processes and represent more of the processes that create uncertainty that we probably presently simply ignore. And I think that's important. As long as we rigorously account for uncertainty along the ways that we learned from weather and ensemble prediction and everything, as long as we apply the same rigor in the principles, I think it can only get better with these systems. Even if uncertainty increases, the result will be a more realistic uncertainty estimate.
All right, Claire.
As long as you know.
All right.
You want to have better models and more realistic physics-based models, and you know, you have to take the uncertainty estimate along. It can only get better.
Peter Steinley from the Bureau of Meteorology is asking, what scope is there for this to be a global undertaking? Alternatively, how much of a risk is there of an overly Eurocentric focus on modeling issues? Is once you can't...
Well, right now there's a year. Yeah. I think it is a global undertaking. You know, the only Eurocentricity right now is that you happen to have have a European funding program that looks at this right now. But I think we always considered this a global enterprise. Actually, before we had Destination Earth, and Peter, you might remember that actually, we had a project called Extreme Earth, which was also, supposed to be funded in Europe, but which was always set up as a global thing, And we're talking to the American community. I mentioned WCRP as a global enterprise, where the Digital Earth is a global thing, So we certainly reach out and want to make this a global effort. It can only be global. It cannot be Euro. I said this is right now only opportunity driven. Just like because the opportunity is there. There's a European Football Championship right now, so that's Eurocentric as well. But I think it's really opportunity driven and not what it should be. It's global.
Thanks, Peter. Here's one from me. You mentioned that climate scientists need to engage with social science questions. So could you give us some examples of the sort of social science questions that you think climate scientists need to engage with?
I don't actually think that we're so far advanced. I think there's a lot of work to do on our side to begin with, because we have to make these workflows interactive. It's not the policy sectors that have to do that. So with our expertise on the Earth system side, and because we are so well organized in our prediction systems, setting up our prediction systems, in coordinating observations and all that, I think we have to do the hard job of bringing this together better. So it's being selective about the models, for example, and destination systems and observations, and the computational science part, which we sit closer to than the policy sectors are. So I think the digital twin framework is still on us, but with this added expertise of computational science, I would argue. But then obviously policy sectors have a steep learning curve, and that means we have to take them along from the start. It can't be like in the past that didn't happen, and that resulted in these linear workflows. We went along and did our systems, and then we confronted them with the data and abandoned them with the data. It's increasingly changing to linear. We have to take them along, because some of their requirements may actually mean that we have to change our workflows or our technical setups or our modeling systems to include some of their requirements at design phase, actually. And so I think most of the charge is probably actually still on us to engage with them and take them along and change our system as they require.
Thanks. Sort of a follow-up on that is, a lot of your diagrams seemed to be Euro-focused. I'm thinking more of the applications here, not so much building the system. I was wondering what plans you had to engage with, if you like, the global East and the global South, and particularly more on the application side, like you're modeling rivers. Are you trying to get in contact with people in those countries whose, livelihoods depend on those rivers, for example? Yeah, things like that.
No, absolutely. We are trying to. I mean, it looks Eurocentric because some of these slides are obviously made for the European Commission that comes up with the funding in the first place, and so we have to have a European focus. Already recognizing that a lot of the European concerns are not limited to Europe. If you think of food shortage and water limitations in the future around Europe, creating political pressure on Europe, it's already a global problem. And that applies to every other area as well. So, even if the slides may have a European bias, it's really only to convince the European Union to invest here. But as I said, by design, this is a global problem. There's no reason why it should be limited to Europe or any other place, really. So what we do in terms of engagement is on the technical side. So on the technical side, in terms of NWP systems and climate systems, all of that is globally organized already. So we engage globally already. We're talking to people in the US and other places for how to do that. And computational science as well. Actually, most computing vendors and technology companies are non-European, which is a great concern in Europe again. But so we have to talk to those, the IBMs, the Intels, the NVIDIAs, all the smart software people, all the big impact sector commercial companies, like food production is global anyway. So it's all that. But then I think an important step is what I showed on one slide about WMO. I mean, WMO increasingly recognizes this, and WCRP is a global enterprise. So there's one slide on Digital Earth I showed where Christian Jakob and I share for now this effort. So that's a global concept. And actually, Christian proposed, maybe one of the regional demonstrators should be an Australian demonstrator, because Australia is very well suited for this, obviously very concerned with extreme weather and extreme weather under climate change. Has a lot of, a very big aura in terms of societal concerns and economic concerns. And maybe that's a very good example. So WCRP and WMO are big outreach opportunities for these concepts.
Thanks so much, Peter. We've come to the end of our Q&A with the general community. And so after this, you'll be taken to the early career researchers who will ask you more questions. And so please remember to go to the other link so you can join Peter. So let's all thank Peter again for a really fascinating and big enterprise that he told us about. Thank you. Bye.
Thanks so much, Craig, and thanks to everybody for the interest.
You're welcome.